Hi and welcome to video 8 on this series of integration required for Unit 4 Topic 1 Specialist Mathematics. We're going to talk about integration using trig identities, and in particular it's probably going to involve mostly substitution rules. And there's lots of different variants in these types of questions and problems, so it's going to be about playing around with the questions, testing different things and making sure that you can deal with and adapt to different situations. So this is exercise 11F. And first of all, these are directly from your formula sheet. Here are some useful trig identities. So first, the Pythagorean identities just here, and they'll be really useful for you, and you'll use those, and you don't even have to memorize or know how to convert. They're all there. And the double angle formulas, typically the other ones that come in most. Maybe angle sum, product identities, but probably not in this case. And also sec and tan are related in integration. So if you derive tan, you get sec squared. And if you integrate sec squared, you get tan. So that's an important relationship you'll need as well. And obviously you'll know sine goes to cos goes to negative sine, etc. So a couple of tips first of all. Integrating cos squared x is quite hard. It's a chain rule type question. Cos x is inside a squared function, and it's pretty hard to do. But we can make this conversion, which I will show you, and integrating cos 2x is much easier. So generally speaking, we want to get the powers out and the multiple angles in. Multiple angles are easy to deal with, powers are hard to deal with. That's a very general rule, and it's not always the case. Sometimes we can be quite clever and set up a nice substitution question, but this is the general case. So let's have a look at that in example 1, A and B, and I'm just hoping I've left myself enough space. So I've got some tips here, and they'll be there for you to refer to as well. So tip 1, sine squared equals a half 1 minus cos 2a. So let's just recall that, and a cos 2a is a really handy one here, and I can see I've got an a there. I probably should have an a here. So I'll pop an a there, a little bit of consistency. So cos 2a is equal to cos squared x minus sine squared x, which you remember from Unit 2, we were able to rearrange this to be cos squared x minus 1 minus cos squared x using the Pythagorean identity, and that's 2 cos squared x minus 1. If we add 1 to both sides, we get cos 2a plus 1 equals 2 cos squared x, and then we can divide by 2 to get a half. Cos 2a plus a half equals cos squared x, which is basically, oh, it shouldn't say, let's say, yeah, that should be a plus. So that's the first one, and we can use similar rules to get to the second one as well. So there's a couple of little helpful ones for you. You have this form of the rule, and if I go back up to here, you can see that here, but you've also got those rearranged versions as well that you can use as you need to. But you might have to take it a little bit further. So in example 1, I can use this information to write down sine to the power of 4x as a half 1 minus cos 2a squared, because sine to the power of 4x is sine squared squared, dx, although I'm taking the a out and putting an x in, so dx, and then I can write this down. I think I'm going to leave a little bit more space. I can write this down as the integral of a quarter, and then in the brackets I've got 1 minus 2 cos 2x minus cos squared 2x, but that becomes a plus, and that's my expansion of this thing squared with respect to x. I can take the quarter at the front, and now I'm going to do a rearrangement of that as well using my cos squared a rule. So I get 1 minus 2 cos 2x plus, and now I've got a half cos 2x, except the inside's 2x, so it's cos 4x plus 1 dx. Now I haven't actually done the integration yet, I'm still simplifying. This becomes 1 minus 2 cos 2x plus a half cos 4x, so that should be cos and then 4x inside, plus a half dx. And almost there, a quarter integral, I've got 1.5 because I've got that plus a half there, minus 2 cos 2x plus a half cos 4x dx. And I've underpredicted here, I need a little bit more space, not a lot more because we're almost done. Now I get a quarter, and when I integrate this, I just get 3x over 2, that's just a linear factor, minus 2 sine, cos goes to sine when you integrate, but I divide by the derivative of the inside, which is 2, plus a half sine 4x, divided by the derivative of the inside, which is 4, and then I've got a plus c, and I'm going to put that quarter in and simplify everything at once. That 2 and the 2 cancel out, a half and 4 make an eighth, but it's going to go further, so I get 3x over 8, 4 times 2 is 8, minus sine 2x over 4 plus sine 4x over 32 plus c. And there's various ways we could represent that as well. But there's my final answer for that integration of sine 4x, or sine to the power of 4x. Okay, that's part A. Let's have a look at part B. And this one's a little bit trickier, and I'm going to use the fact that sine squared x is equal to 1 minus cos squared x. And I'm going to show you another little rule here that will help us out. So, let's start by writing this down as sine x times sine squared x cos to the power of 5x. I've just done that split up, and this is what happens if I've got odd powers rather than even powers. I'm going to end up with this additional sine x power here. It works out quite nicely, but it doesn't look like it at the moment. 1 minus cos squared x cos to the power of 5x dx. And now I expand this bracket out, and it gives me sine x cos to the power of 5x minus sine x cos to the power of 7x dx. And I'm going to actually split this up. I could factorize, but it actually is a bit easier to split up and work on those two as separate functions to make my situation work. So I'm going to write this down as sine x cos to the 5x dx minus the integral of okay, now I'm going to recognize here that, yeah, I've got two separate terms. I could split this up, but I've got a simple u choice that I can make. So this is the odd power situation. And what I'm going to do over here is I'm going to say let u, this is substitution now, equal cos x. And it works in both cases. So if u equals cos x, then hopefully you can see that du dx is equal to negative sine x, which means that dx is equal to du, or negative du, over sine x. And so now I'm going to put that back into here and write this. The integral of sine x times u to the power of 5 minus sine x times u to the power of 7 times by du over sine x, and of course that's negative. Now I'm going to bring the negative out the front, and the sine x will cancel with that sine x, which is handy, and I'm left with u to the power of 5 minus u to the power of 7 du, which I could provide as u to the power of 7 minus u to the power of 5. And so I will do that expansion now, u to the power of 7 minus u to the power of 5 du, and that of course is equal to 1/8 u to the power of 8 minus 1/6 u to the power of 6 plus c, which is equal to 1/8 U is cos x, so cos to the power of 8x minus 1/6 cos to the power of 6x plus some constant c. So there we have a couple of examples of using trig substitutions and trig identities to simplify integration so that they become integratable functions. All the best.